To welcome you to our April STEMinar, sponsored by STEM Corps. And I'm happy to see members of the PER group are here today as well. So our speaker today is Stacy Lowery Bretz. And although this is the first time I think we've actually met, I've been very aware of Stacy's work for about the last 15 years or so. She got her undergraduate degree in chemistry at Cornell University, and then went to Penn State for a master's degree in chemistry as well, and did work in organometallic chemistry, and then was sort of bitten by the chem ed bug, I guess, maybe is kind of the way to say it, and then went back to Cornell to get her PhD in chemistry education. She also did a postdoc with Stacy at Berkeley as well. She has a sort of an amazing list of recognitions and honors, and I'll just mention a couple of them. First, she's on the editorial board for the Journal of Chemical Education, the sort of flagship institution for chem ed. She's a university distinguished professor at Miami University of Ohio, not the Miami in Florida, but the one in Oxford. She has been the chair of the Board of Trustees for the American Chemical Society Exam Institute. She's a fellow of the American Chemical Society and also a fellow of AAAS. And she's been chair of the Chemical Education Gordon Research Conference. And so these are things that only people who are very well versed and well known in the community and who do solid research as a result get to see. So we're very honored to have Stacy here, and she's going to talk to us today about inquiry and meaningful learning in the undergraduate chemistry laboratory. She's already given us a great talk at the chemistry department about meaningful learning in the classroom. So this will take us now to the laboratory part. So Stacy, take it away.
Thank you, Don, for your very kind introduction. Hi, everybody.
Hi.
Okay, participation is required, not optional. So, hi, everybody. Hi. Okay, so I would benefit from knowing who's in the room. So, like, graduate student, faculty, discipline, what XER you do if you do DBER of some kind. So, could we just go around and quickly introduce ourselves? And I have a feeling maybe not all of you might know each other as well. I'm not sure about that. So. We'll start in the back and work our way forward.
I'm Jessica Spott. I'm on staff here, and I work for the STEM Center.
Okay. Do you have a discipline home that you claim?
Actually, both of my backgrounds are in communications,
okay.
So not STEM
Great.
at all, but I do work for the STEM Center, so I have gleaned a lot over the years.
Great.
John Chattosin from chemistry.
I'm Ken Griffith. I run the STEM pedagogical program here in the Teaching Learning Professional Development Center, and I'm a biologist too.
Biologist, great.
And Brock Williams from math.
I'm Jessie Simpson, a STEM librarian.
Okay, great. Go ahead.
George Page, chemistry graduate student.
Okay.
I'm Miranda Andrews. I'm also a chemistry graduate student.
Greg Lane, chemistry department.
Dominic Casadante, director of STEM Corps and also in chemistry background.
Great.
Prudence Venner, geoscience grad student.
Okay.
I'm Beth Becker, physics faculty, physics education research.
Great.
I'm Stephanie Hart. I work in the provost office and I run a dual enrollment STEM-based program.
Okay. Great. Have we met before?
We might have, I don't know.
Did you work with John Novak?
No.
Okay.
No.
All right. I was at a conference once where somebody came up to me and said they were his first graduate student and I was his last graduate student. And you look like okay. All right. I am happy to stop and have discussion and Q&A as we go. You don't have to sit there quietly. Feel free to interrupt with questions. So I've been doing research about laboratory learning either by myself or in collaboration with my colleague Marcy Towns at Purdue University for over 15 years or so, and so I just brought some highlights of this. So okay, so I want to start with a question that in my state of Ohio, There's not enough money to fund all the public education needs, and that's really gotten a lot of press in the news in the last month at the K-12 level. But higher education is in the hot seat too, and there's always a pressure to where can we cut costs, where can we cut costs, right? So, if you were a dean sitting in this room, or a department chair, and the dean came to you and was like, you have to cut, 10% of your budget, like where would you get that money from? Okay. And I would like to suggest to you that, also this does not work on, again, we have one of these screens in my department too. It's disorienting. You're used to shining a laser and it comes back at you. That's fine. Forgive me if I do that out of reflex and have to relearn that lesson a few times this afternoon. That laboratory learning is exceptionally expensive. So I don't know the dollars and cents of every discipline that's been mentioned here this afternoon, but in a chemistry department, laboratory instruction requires very specialized spaces. It requires the use of consumable chemicals that can't be reused. We generate waste that has to be disposed of in a special manner. We typically provide instruction in the form of graduate students who require stipends and tuition waivers. And you can imagine an argument that could be made that this space is especially expensive. We don't even use it every hour of the day, right? How many of you had a space audit before? Oh, those are great fun, and by great I mean not. They bring somebody through who knows nothing about science, nothing about STEM at all, and they're literally counting, there's 24 hours in a day, 7 days a week, how often are students in this room? And so they'll look at this and they'll go, this space is underutilized. And then you explain, well, we can only use it when graduate students aren't taking their own classes because they have to help teach, and you have to have downtime where you're changing over the rooms because we literally don't have one room for every course. And you go through all the explanations and they just go, you only use this 42% of the week. It's not even half the week. We need to find a way to use this space more efficiently. At which point I usually say to them, do you want a home? Do you rent an apartment? And they look at me like, what? And I'm like, do you have a bathroom? Yes. Are you in the bathroom more than 50% of the week? Because if you are, and I'm just suggesting that nobody would build a home without a kitchen or a bathroom, and these are highly specialized spaces, but you wouldn't have this expectation that you would be using them all the time, right? So nonetheless, there are people counting dollars, and the reason that this is in the hot seat is we don't actually have data that we can use to defend our use of this money in these spaces. So this has been reviewed in lots of different disciplines. Reed and Shaw's work is generally across science education. We just assume that it's an important activity because no self-respecting scientist could ever imagine not having laboratory courses. And by laboratory, I mean quite broadly here, right? Like field, outdoor experiences, as well as wet lab or computational dry lab, things like that. Like it just never even occurs to us to think of teaching science without a lab. But other people are asking those questions because we don't have data between learning that show the money spent here results in student learning. And this last quote's actually from the Australian Council of Deans. So the people who are supposed to advocate for the science saying, do we actually even need this? Couldn't we just do something with a simulation or an animation online and save everybody a bunch of money and a bunch of time? Think what we could do to save that money. So I had the privilege a few years ago to serve on NRC panel that looked at discipline-based education research, and hopefully most of you in this room have seen this report. And we looked at what did we know about laboratory learning across each of the disciplines in DBER, physics and geosciences and biology. Math was not in the DBER report. We take a lot of heat for that because it's not in there, and like what was our problem with math? I will just say two things. One, we were charged to do this by the NSF and they didn't ask for math, and you don't get to change the charge for the NRC. That's the way, so it's not us, it's them. That's a weak argument. The more substantive argument is that math is something that students learn from pre-K on up. And these disciplines often don't have identities until secondary school or college. And so we, I think the reason NSF tasked us to look at these sciences and engineering was because they wanted to know how these disciplines emerge in the students' learning as opposed to math, which has a very different lifetime in the student's experience. So it's not that there's not math education research that was not worthy of being included. It was literally the charge to look at sciences and engineering. So I have some really good friends in math ed who don't like either of those explanations, but that's what I got. So there's been very little research about this laboratory learning. Part of the problem with measuring learning is we don't have good instruments, and that's where my group's work comes in. And there's been very little research about the affective domain, and one of the things I hope to convince you of this afternoon is that we ignore affect at our own peril. It's not something most scientists and engineers are used to thinking about. Like, we tend to think of STEM as this objective discipline. There should be room for emotion or attitude or feeling about that, but I hope to persuade you otherwise. So this is how I think most of us expect lab to go, and you could just take out the word chemistry and put in your own discipline there. Faculty have goals that they want to be achieved. They design a curriculum so that students can meet those learning objectives. And then the students come in with their expectations about lab, we reshape them, and they exit with these experiences that demonstrate that they've met these goals. That's how we expect it to happen. And the research I've been doing in collaboration with Marcy and in our group over the last 15 to 20 years would suggest there's a few little hiccups in how those gears work together. So in the late 2000s, we published a series of papers where we had interviewed dozens and dozens of faculty about what were their goals for the undergraduate chemistry laboratory. And we talked to faculty who had had funding through the National Science Foundation to make changes. Like, we wanted to, what were they dissatisfied with? Why did they want to do something better? That was part of our sampling mechanism. And then we also talked to faculty from institutions where, as far as we could tell from the NSF awards database, they'd had no money for making changes in their curriculum go to that department for at least 10 years. So it was our proxy for the status quo, right? Things were acceptable for them in some fashion there. And so we published these papers describing what faculty wanted to have happen, what they saw as things that got in their way, what they thought learning looked like in the laboratory. And then Marcy's group, this paper at the bottom here, took those interviews and turned it into a survey so that we could measure across the country with more faculty how many of them also shared these goals. And just to highlight from what we found there, there's certainly some goals in common. Everybody mentions laboratory technique and the ever popular critical thinking. We can all say it, nobody really knows how to measure it or what it would look like when we see it. And then there were some things that varied by whether you were teaching an introductory course or whether you were teaching upper division students. Not too surprising there. But then we went to look at that second cog in the design of the curriculum. We went to look at their curriculum. And so we created a rubric that characterizes the degree of inquiry or degrees of freedom that students have in an experiment to make choices about what data to collect, what problem to investigate, how to analyze it, how to report their data out. And we actually analyzed a whole bunch of laboratory curricula across different disciplines. So I just want to show you a snapshot of some of these. So in this paper in the Science Teacher, which is actually the National Science Teacher Association publication for high school science teachers, we had a discussion about, well, if you're going to do inquiry, what ought that look like? Where should you start them? And some people argue that you should start at the beginning of the school year and ramp it up. Some people look at this curve on the left and think, no, this is what I want to do over 4 years. Like, I want my freshman experience to be lower in inquiry. And some people are like, no, you can't just take them through that once. They need to have multiple cycles in each course or in each year so that they understand, as they engage with different content, what this inquiry would look like. And the problem is everybody's using this word inquiry, and it means very different things to different people. So this is what the rubric looks like that we published. And across the top, you'll see we have different labels for these different degrees of freedom. And then down the left side here, different criteria, where you can provide more structure or less structure for your students to think about these things. And there's good reasons why faculty gravitate towards level 0. There's lots of good reasons there. There's less likely to be accidents. There's less likely to be waste, which is a cost. It helps you figure out how to train your graduate assistants as TAs, because their job is to make sure that the students don't hurt themselves and that they carry out the physical manipulations with fidelity. But then you have to ask yourself, is that actually what scientists do? No, that's not what we do. And so it's not giving our students the opportunity to actually experience our discipline. And they're like, well, if this is already figured out, I already know what the answer is before I've even started. I'm going to be worried about making mistakes. We plan the experiments to last the whole 3 hours long. We don't give them a chance to make a mistake, identify the mistake, try again. We penalize them for making mistakes. We ask them about the purity of their compound or what their yield is, and we penalize them. And so we put them in these impossible learning experiences where any mistake is going to come with a penalty, and encourages them to cheat to avoid the penalty. And have they really left understanding what we want out of science, which is, how do you do experimental design? What do you do with error? How much precision or accuracy is in your data? So this is one of those infamous slides where the person says to you, I don't want you to read this. What I'm going to tell you I want you to see here is that we looked at laboratories in these disciplines in the bars. I can't point it out with my pointer. So astronomy, biology, chemistry, geology, meteorology, physical science, and physics. All these lab manuals marketed themselves as inquiry experiences for their students. And so we sampled 386 experiments out of these books, and we have columns here of the degrees of inquiry. And what I want you to see is that the most filled in column is either 0 or 1/2. The actual structured inquiry, guided inquiry, authentic inquiry columns are essentially empty. And these are materials that all market themselves as providing these inquiry experiences for students. So we're not really sure that we know what inquiry is when we talk with a colleague about, yeah, I do inquiry too. What does that mean? What does that look like? Okay, so we talked about faculty goals and curriculum. And what I want to spend the rest of the time with you this afternoon on is this third cog, which in many ways ought to be the one that's driving the other two. Not from the top down, but from the bottom up. So the theory that we use to examine our work is from David Osseville and Joe Novak, who are cognitive psychologists. It's a theory of meaningful learning. How many people in the room are already familiar with this? 2 people. Okay. So let me just, if there were lots of hands, I would have just moved on. Okay. So this theory of how human beings learn says that you need to have experiences in 3 different domains: cognitive, affective, psychomotor, thinking, feeling, and doing. And it's only when those are integrated that meaningful learning happens. If you're missing some of those, then the brain resorts to rote memorization as a way to hold on to information. Meaningful learning is making substantive connections between what you already know, your prior knowledge, and what you need to know. And you achieve that through these kinds of experiences. So when we think about what this looks like in a laboratory, the doing part is pretty obvious. You're collecting samples, you're collecting data, it's inherently visible. But what evidence do you have that your students are thinking? What evidence do you have about the affect? Like, that one's a real,
Yeah.
most scientists are like, no, that has nothing to do with lab. I would like them to make a connection between thinking and doing, but that doesn't belong there. Well, we actually have molecular level evidence, so this is what I dream of. I dream that I will have like a functional MRI that I can just like run my students through. That'll never happen. I'll never get approval for that from the IRB. But there are places where they do that, and they've done studies of the role of affect. So they've taken children who are in late elementary, early middle schools, like grades 4 to 8, and they have made these groups equivalent in all ways that they can, except for fear of mathematics. Half the children are math fearful and half love math. and they gave them math problems to solve inside a functional MRI. And you can actually see different evidence at the molecular level in the metabolism in the amygdala. That's the emotional center of your brain. And so what studies like this point out to us is that the amygdala, that emotional center of our brain, actually controls access to the cognitive processes. It's the gatekeeper. Stuff either gets in because we're interested, or it gets blocked because we're uninterested or we're fearful. It's this gatekeeper of the in or out. And so if we want meaningful learning to happen, if we truly want this connection between the cognitive and the psychomotor to be formed, we have to pay attention to this affect that students are going to bring to our experiences. And if we don't know what their affect is, then we do that at our own peril. Make sense? Yeah, Tom?
So I've done some encephalographic studies that also actually confirms this exact point as well. And it was with an expert novice paradigm rather than, but the affective is extremely important.
Yeah, and I think it's great now that we have molecular level evidence of that, right? To counteract those who are a little suspicious about it. Okay, so how are we going to get at this cognitive and affective, which are not as visible as the doing in our laboratory? So some large questions that have driven, yeah, go ahead.
Well, the cognitive, I've always seen that as being like the lab reports.
Okay.
That's how we would measure that.
Yeah.
How well they're explaining what's going on in the lab reports.
Do you find anything dissatisfying about lab reports when it comes to like telling you whether a student truly understood what they're doing?
Well, they could always copy it off the internet.
Yeah.
I run into that too often.
Yeah. Or they can copy it out of the introduction to the lab at the beginning. There's a lot of,
happens way too often.
right?
As well.
So when we're talking about degrees of inquiry, this rubric that we use, some faculty feel like I just have to tell them everything up front that they need to know. My introduction has to be really long, and then they're going to go in and they're going to confirm this and see that it was right. Yeah, so they get it from there too. Yeah, go ahead.
So, I guess I understand your diagram here. I'm curious, I'm trying to understand what your research questions, okay, so the research questions are to explore these things, and but more explicitly your question is, how are then these things measurable?
Right. Right, so I want to know what the student's cognitive and affective experiences are, but I have to have a way to measure that. And so what I'm going to share with you is the story of how we came up with a tool to measure it.
Okay.
Okay? Sure. And we wanted to know not only just what their experiences were post some course, we wanted to know what did they expect coming in. Okay? And then we wanted to look at that sort of longitudinally. Like what happens when a student moves from sophomore to, or freshman into sophomore, et cetera. So the design we have for the study, as we did what's called sequential explanatory, so both qualitative and quantitative, but we use the one to drive the other. So first we made the instrument based on the theory, which is the exact opposite of the talk I gave this morning, for those of you who were here this morning. We did it the other way around. And then we piloted it, and then we used scores on that instrument to invite people to participate in a qualitative data study where we observed them in the laboratory by videoing them, and then we invited them in to talk about their experience in the laboratory and to narrate some of what they were thinking during the video clips. Okay? So I'm going to share with you data from all of this. So a little bit about the video part first, because I'm going to focus mostly on the quantitative stuff. So we gave them like action cameras to wear, right, on their body, on their forehead, and we also had stationary cameras in the room, and they forget about it after a while. And so there's lots of things you hear that the students are like, the graduate students are like, do I need to transcribe about their date last night? And it was like, no, you can just put parentheses, student discuss what they did last night, and move on. So they really do forget they're wearing them. Like, I didn't need to know that. Just a little too much information. But you see all kinds of stuff. Like this student in the upper right corner up here is about to scrape some of their sample off the bench top and back into there because they spilled some. And they're going to get a penalty for a lower yield. Never mind about what else might have been on the bench top. this student down here is using the edge of a piece of paper to draw a straight edge instead of a ruler so they can do TLC, thin layer chromatography. You can see when they're going back and forth, are they consulting their neighbor? What are they looking at for references? Wow, is it eye-opening to just watch from the point of view of students what they do.
I would give a lot to have cameras on my students, honestly.
Yeah, and then we have one in the balance room, so we have a balance where they can take masses in between two rooms, and we have one in there. So they go out of the eye shot and ear shot of the TA, and then all kinds of hell breaks loose in there. Because that's how they talk about what was really going. Do you even know what we're doing today? No, I don't know what we're doing. So learn all kinds of stuff. This is all IRB approved, right? Like we have human subjects approval for all of this. So what did we do? We asked the students to come in for an interview with us within 24 hours of their videotape lab experiment. And we asked them a couple questions. Could you pick out a time during the lab where you felt you were learning something? And so we would advance to that part of the video, and we had them narrate, like, how did you know you were learning something? What were you learning? And then we would ask them, when was a time in the lab yesterday where you were confused? Didn't know what was going on, weren't sure what to do next, and same thing, we go to that, etc. And we also gave them this word matrix that we came up. This comes from the literature in psychology about different affects that students can have. And we asked them to cross out words that never apply to their experience in lab, circle words that sort of always apply, put some stars.
Organized is crossed out.
What one's crossed out?
Organized.
Organized, yeah. So put some stars by things that apply particularly to the episode we videotaped yesterday, because in our pilot interviews, when we would ask students, how did you feel about lab yesterday? Nobody answers that question. How did you feel? Like, it's too threatening, it's too personal. They don't even have a vocabulary to talk about that. So this matrix was a way to give them a vocabulary to say, no, I never feel interested in lab. Or I'm always confused, right? So it got them talking, and that was the point of this prompt. So this is, pardon me? Are we good? So this is some data from these interviews. I think we interviewed 30 students in this, and which ones did they choose? They chose. So the blue is they circled. I always feel this. The orange is the X'd out, and then there were words that were neither circled nor crossed out, and that's the green. And they're just sorted from most circled to least circled. So this was very effective at getting them to talk, much better than asking, how did you feel in lab yesterday? Which was a short conversation. So,
were you surprised that the most popular or positive, meaning the blue, was interested?
Yeah, so that's a good sign, right? Like they come to lab interested. So this perception that's cynical, I won't speak for the rest of the disciplines in the room, but as a chemist, the cynics in us are like, students don't want to be in lab. You know, we get jaded very quickly. This is like a poke, like, no, they're not. That's your perception, that's not their perception. Where did you get that perception from, Professor Bretz? Like, how did you come to be so cynical? Why are you imposing that on your students who are new every year? So this
evaluations.
Actually, my evaluations are great. So,
No, I'm just saying that's stuff that comes in the free response part of
yeah.
evaluation.
So this matrix was good for getting them to talk, and it was good, like as a teacher, to remind me that it's new for my students every year. Yeah.
Okay, and this matrix was based on, did it have a predecessor for a metacognitive tool of some sort? Was that by Galloway?
The reference that we got on affect is actually cited in these two papers that we published.
So they were using this matrix, or
no.
So it was based upon this matrix?
We drew it, we created this matrix from other literature we'd read in cognitive psychology.
Okay.
Okay. Okay, I had an undergraduate research student who was majoring in social psychology, and he took this class and he said, have you read this paper? And I said, no, and it's the best of all things, right? So the student brings it to me, I'm like, wow, this vocabulary would be really useful. We're having a hard time getting students to talk about this in our interviews, and so we came up with the idea of this matrix, and we decided what words to pick.
And maybe you'll go into this later on in your presentation. Did you use any other tools to measure effective?
Yeah.
Okay. All right.
So this was the qualitative piece with the videos, and that's really all I'm going to say about this. I could give an entire talk about that, but I want to talk about the quantitative piece. So using the theory of the cognitive and affective psychomotor, we decided we wanted to make a tool that could measure. So before I turned into somebody who does chem ed research, I was an analytical chemist. I worry a lot about precision and accuracy, or what's called reliability and validity in the social science language. And we can't tell if we're doing any better if we don't have tools to measure things with, right? We need something to pick up signal. We need a way to discriminate between signal and noise. And so this is what my research group does. We make measurement tools. We show that they generate reliable and valid data in certain contexts. And then we publish them with hopes that other people can adapt them to their own instructional needs. So if you're designing an intervention in pedagogy or curriculum, then you have a way to either measure baseline data and show a change, or run a control experiment, whatever your design might be. So this is called the MILI. That's how I refer to it, meaningful learning in the laboratory instrument. And we give the MILI as a pre-test, post-test. So before the course starts, we want to measure students' expectations for laboratory learning. And then we're going to measure, when the course is done, what their experiences were. So this pre-test has to be given before they do any experiments in the course. And we try to do the post-test at checkout. Right? So when you're doing human subjects research, there's also a little negotiating with access to the instructor, but we try to get them as close to the end of the semester as we can. And so when we first made MILI, we had a whole bunch of items because we didn't know what to ask. 78 is way too long for anybody. An indicator item says, mark this answer to this question, so that we could be sure that students were reading each item. And we did it online, we did it with paper, we did it with Gen Chem, that's GC, and OChem is organic. We collected it at different institutions. We used exploratory factor analysis to help us identify which items were redundant, so we could eliminate some, but also keep some, so that we could see if students answered them consistently, and we retained them. And then we used our theory to decide how we were going to shorten that down. And ultimately, MILI ends up to be 30 items with one indicator item. And we decided we were going to administer it online, although you can give it on paper. And so, I don't know what survey software you guys have here. SurveyMonkey, Qualtrics. Qualtrics? Yeah, I mean, they're the same thing, right? So, we use a slider bar, and I'll show you that in a second, for students to respond, so it's interactive. And then we did response validity interviews with students. We had to come in and answer it in front of us. Why did you choose that? What do you think this question is asking you? So that we can make sure that everything was interpreted accurately. And then we rated each item on the MILI as either an item about cognitive, an item about affect, or an item about C/A, both. Now you'll notice there's no psychomotor items up there. We tried to write items that were just psychomotor, and we found it impossible. Like, you have this theory, you think this is the task I will do. It's impossible to write an item about just the doing without some sort of thinking attached to it. So ultimately what we did is we put the thinking in the STEM when I'm in the laboratory, and then we asked about cognitive and affect. Okay? So we ended up with these items across those 3 scales, cognitive, affective, C/A. And here's some example items. So cognitive might be, I expect to make decisions about what data to collect. I expect to worry about the quality of my data, right? So that's a C/A item, because the worry is the affect, the judgment of quality is a cognitive. And that word worry turns out to be really fascinating, because later I'm going to show you some data where we asked faculty, do you want your students to worry about the data? So the higher your score on MILI, the better. So if something is negatively worded, right? Like, I expect to focus on procedures, not concepts. That's less towards meaningful learning. That's more of a rote approach to it. So we reverse code those items, so a higher score is always better. And then we gave each student an average on each scale. So this is what MILI might look like when a student logs in. The STEM is the same for every question at the top. When performing experiments, it says, I expect to, and then they take the slider bar and they drag it out. Excuse me. If you want to say 0% agree, right, that I completely disagree with this, you have to drag it out and drag it back. Qualtrics marks it as a non-response if you just leave it at 0. And then at the end of the semester, it said, when performing experiments in my chemistry lab this semester, I experienced, so we changed it to the past tense. Occasionally we had to make a grammatical edit in the wording to account for it being in past tense, but otherwise most of the items stay the same. Okay, so I'm talking to STEM ed researchers, so I'll put this slide in here. So our first data set was 614 people who we had matched responses to pre-post, so we could match them as individuals. And this is the Chromebook alpha for each of these subscales. And so in general in the literature, there's a cutoff of about 0.7 being pointed to is indicative of we should trust your data, that it's reliable. And if it's below 0.7, the traditional interpretation has been, you need to fix your measurement. It's not good enough, the data's not reliable. So if you look up here, you'll see that the C and the A are both above that, as is the total, but this C/A is below that. So a surface interpretation might be that we need to work on rewording those items. But I would propose to you that what that actually suggests here, and we have some references below here by Wendy Adams and Carl Wyman, as well as a paper that I published in JChemEd, that the application of 0.7 as this magic threshold has been problematic. That comes from a scale where all items are about one thing and you have a constant affect towards them. When you're measuring something where it's about more than one item and you don't have a constant affect, like it's not your political leanings or how you spend money, something like that, you're going to respond differently, and in the calculation of this number, that will come out as a lower alpha. And so in fact, with an alternative interpretation here of this 0.6 is that it suggests that the cognitive and the affective are not well integrated or connected in the student's mind, and that's why it's a lower number. Okay, so my little mini lesson for the graduate students on don't just blindly apply statistics. You got to think about what you're doing. Yeah, down.
So if you were to do this, let's say, for seniors versus freshmen, would you expect the cognitive/affect to be?
Yeah, are they all majors?
Yeah, let's assume it's a homogeneous group if you're doing it for.
Well, in an ideal world, it would be better for the seniors because it would be well integrated. But as a practical manner, I'm going to suggest there's not much difference.
Okay.
I'm sorry, I hate to be cynical. Okay, so I'm going to share with you the results of some studies. One we did at my institution where we measured pre and post, and they're in between they had a treatment of course. Then we did that nationally, and so you can see here the sample sizes for these. And then we wanted to do a longitudinal study, which is very hard to do because I'm not allowed to plant chips in my students and follow them around, and I can't force them to take lab courses so that they'll have the experience I'd like to measure signal from. So I'm going to talk to you about each of these studies. So here's data from an item on the milli for this first study that we just did at Miami. I expect to consider if my data makes sense. So can you see that okay? I can't tell what the light looks like. Okay. So a couple things about these graphs. You're going to have spikes at the 10s and the 5s because that's just an affectation of people drawing it out and dropping the bar. This is not like some mass spectrum where I'm going to attach meaning to an 89 versus an 88 or something like that. So, students say, sure, that's a reasonable expectation to have. And if you break that out by Gen Chem, so GC at the top and organic chemistry, OChem at the bottom, really doesn't look that much difference for students who've already had a year of experience with laboratories. I expect to feel intimidated. That looks very different than the previous slide, right? So clearly we have a range here, and you think, well, maybe these are the freshmen who just don't know how lab works, and the sophomores who are in organic chemistry are okay. And if you break that out, no, that's actually not true. This is the 100% down here for the OChem. Like, that's a head scratcher as a faculty member. Like, that's not good. These are the people who are going on. Like, they're already in OChem. Think of all the people who, dropped out, withdrew. We didn't retain. I expect to learn chemistry that will be useful in my life. I learned chemistry that was useful in my life. That's just depressing. This is the kind of thing where your chair or your dean should come to you and go, what are you doing? These students come in, look at me pointing with my laser pointer, they come in expecting this, and we do not meet their expectation in any way. Of course, from a histogram, you can't match people up, so then if you make a scatter plot, you can, right? And so the x-axis here is always going to be the expectations or the pre, and the y-axis is always going to be the experiences or the post. And then I just have a y equals x line in there. What these graphs don't show you is 3D, so I don't have an n, right? So the depth of how many people are represented by each dot. But clearly, most of the data is below the y equals x line for almost all our individuals. Their experiences did not live up to their expectations. Any questions about these? Because I'm going to show you more of these. Okay. I expect to think about what the molecules are doing. Like, this seems essential to me as a chemist, that if I'm going to ask you to weigh something out and measure it and mix it with something else, and then tell me something about what you've made, which is a generic gross oversimplification of lab, that at some point it ought to occur to you, what molecules are here, what molecules are there, how did they get from here to there and undergo this transformation. So students know that they're going to be expected to do this. I thought about what the molecules were doing. So how is it that you get through an entire semester of college chemistry laboratory and you haven't thought about them? Whose fault is that? Yeah, that's a faculty decision. That means we never assessed them on it. Because if we had asked them for that in the lab report or on the exam, and we had put points about it, you know darn well in the economy of points they'd have done whatever we asked them for the sake of a few points. So here they are. I'm going to take chemistry. I'm going to think about molecules. I thought about molecules. That's shameful. This is my own institution. By the way, I had to give this talk at my own institution. When I got promoted to University Distinguished Professor, my chair said, well, now you have to give a talk to the department about what you've been doing for research. And this is the talk I chose. I was promoted to University Distinguished Professor. What are they going to do to me now? So, and here's the scatter plot for that. Okay, so like I said, we gave each student a cognitive average, pre and post, an affect, and a C/A. And so now what I have here is pre is still X, post is still Y. This is their composite average per student. And I've still got a Y equals X line in there, okay? So it's hard to tell really much from the cognitive slide. They're all pretty much bunched together, but when I show you the affective slide, you're gonna see the difference. So the affect is much more spread out. And we thought about this for a while. My university is a highly selective undergraduate institution. The average ACT is 28 to 29. We're a residential campus. The average time to degree is 3.7. We retain over 85% of our first year students go on to the second year. So, I mean, it's a good place to work. You have really bright students. But all of our selection mechanism is based on their cognitive experiences, right? Test scores, letters of recommendation, all that sort of stuff. We don't select for affect in the admissions, at least as not as I'm aware. And so it shouldn't be surprising that there's more bunching, right? Like students come from AP and IB experiences, they don't have as much variation in their cognitive as they do apparently in their affect. What that says to me is, I can't do much about the cognitive they come with, but that affect gives me a lot of opportunity to think about leverage to change their experience because there's more variance there. And then the C/A is in between. And that's something we found the whole way through the study, that it resembles neither extreme, but the mixing of them. And then this is the OChem. So you'll notice I had 800 students in the pre and post on the design slide page, but this is what we ended up with matched pairs, right? So between OChem and Gen Chem, we ended up with just a little over 600 of the 840 students could we actually pair people. They took both of them, we could read their signature, we could actually, pair them up. So you asked me what happens when this is not seniors, and these are not the same human beings, right? This is cross-sectional data, this is in the same calendar year, but these people are a proxy for who those people are going to become the next year, right? It's not better. And in fact, I'd suggest the affect looks a little worse there. So we wanted to know more about these changes. So we created these things that we call vector plots. We've never seen them published anywhere else in the literature. If somebody has seen these before, I'm happy to know what they're called. And what we did is we took the top 5% of the people who reported the highest cognitive experiences, right? So how is it in the same course that you have this student, I can't use my pointer, you have a student way up there in the top right-hand corner of that graph who's like, this was fabulous, right? And then you got a student way down here, like in the same course. That seems like a big variance. So we wanted to know more about that. So we looked for the people who had the highest post-cognitive averages. The people, the top 5% who said this was the best that it went. And their post are in orange, and then we mapped their pre. So we looked at that for a little bit, and we thought, well, some of them had lower expectations and things went better than they want. Some of them, we still didn't meet their expectations. Then we said, well, what's this look like for the affect? Oh, I'm sorry, this is the bottom cognitive. The affect's on the next slide. So these orange dots are the people with the lowest cognitive post experiences. And here's where they started with their expectations. So those people who told us it went the worst didn't just start with low expectations, right? The magnitude of those vectors is pretty long. They came in having expectations that this was going to be a great cognitive experience, but we didn't live up to those expectations. And then I want to show you the affect. So these are the highest affect in orange, post, and where they started. So for the most part, things got better than what they expected. And these are the lowest affect. So again, I'm really struck by just how the magnitude of those vectors, just how long they are. It's disheartening to me as a professor. Here are kids coming in who really are like, teach me, I am ready for this. And it's just the cart, the wheels have come off the cart, yeah.
The highest and lowest, by what proportion?
Top 5%, bottom 5%,
Thank you.
of the scores we had.
Question?
Yeah.
Is there any correlation with grades in the class?
Yeah, so I get asked that question a lot, and I don't have any grade data, and I'll tell you why. One is from a human subject's point of view,
Yeah.
but more importantly, it has to do with the grading practices. So we have TAs, some of whom are English native speaking, and some are not, and we require every laboratory section to be normalized to the same grade. So now that really makes a grade meaningless to me, because I'm enforcing a normalization process on my laboratory section for a completely different pedagogical reason. Actually, I'd suggest there's no pedagogical reason there. But this policy is in place, and so it makes grade data meaningless. So I can't match it to grades, and at my own institution, I wouldn't even spend the time doing it.
Just a quick question, top 5%, bottom 5%, that's at the end, right? Those are the orange dots?
Yeah.
So it's sort of built into the two graphs that the orange dots will be low numbers for the bottom 5%. And you want to see how they got to, how they transferred, how they traveled to the low numbers. So that means, and that's the orange dot is in the 5. So that's built in as a high enough, that's high on the graph, right?
Yeah.
And on the other one, the orange is built in low on the graph because that's who you
Right,
select.
the axes are the
Yeah, but
same.
they're
It's
starting
their
to-
cognitive
No,
average.
you're just trying to see how they travel to be
Yeah.
low and how they travel to be high.
Right, so the axes here are cognitive on the X and affect on the Y, and I'm
Yeah.
looking to see where they moved.
But it would be hard to travel up to the lowest because you're already starting at the low end of the scale. It's hard to get below it.
You could have stayed low.
Yeah, but it'd be hard to travel. I mean, in a sense, you would expect the drift to be a down because you're picking a low end point because you can't be below it when you start because you're saying ending low.
That's not theoretically
Oh.
impossible. This data suggests nobody does that. I'm looking. No,
Oh,
so
see-
here's one. The
Well,
one
no,
that-
yeah, I'm just saying in a general sense, if you're saying the bottom, we're rating things in the bottom 5% at the end, there's not
not
a lot of
Here's
contrast
this
on
person
the
right
scale
here.
to be below it.
Here's this person.
Yeah, I'm
It
not saying
starts
no
higher,
one. I'm not
and
saying
ends
no
lower.
one, but yeah.
Okay, so
And this is evaluated on could you clarify, on a Likert? Is that,
no, they drag the.
and it's a sliding bar. So
Sliding bar.
It's a demi Likert.
No, I'm really going to reject that Likert scale because actually I've read some first of all, it's not Likert because it's not categories.
Because it's not a rubric isn't applied to that.
I'm not saying strongly agree, I'm not using categories, I'm using or 0 to 100 so they can give me whatever precision they want.
Okay, So
The other reason it's not a Likert scale is I've recently read papers that suggest that that's also completely misused, because that is only ever supposed to be used for a unidimensional scale, and people misuse it all the time because they use the response option of strongly agree to strongly disagree, and that's what triggers the label of Likert, and that's not what a Likert scale is. So
they're under an so basically by prior exposure to Likert-like evaluations, they'll still evaluate those based on that prior experience.
When we do the response process validity interviews, I don't have this slide here with me. We actually look at, do students use the whole range? Because we were worried like maybe some students just use this part of the range and some use this. And you can see that the students use the entire range. So they discriminate amongst these items by the extent to which they agree or disagree with it. But we did not make categories for them to fall in. We've only labeled the 2 endpoints, completely agree, completely disagree. Okay, so then what we did is these vector plots suggested to us that there's groups of students having different kinds of experiences, right? So looking at a histogram or a scatter plot really doesn't give us a handle on what, that's just a composite over the whole thing. And so we wanted to know more about these groups of students. And so we turned to cluster analysis. And we did, how many people have actually done cluster analysis in the room? Anybody? Okay, so it's a technique that's used in all kinds of disciplines. It's to take a large data set for human beings and try to identify people who are most like each other. So I could take 600 students here, and I would do an analysis based on their cognitive average and their affective average for pre and post, so 4 variables. And I'm going to take those 600 students, and they're going to be put into 600 dimensional space. So each student is a cluster of 1. And then I'm going to ask the computer algorithm, using these 4 variables that I've identified, which 2 people are most alike. And they're going to put them together into a cluster of 2 people. So now I have that, and everybody else is still a cluster of 1. And then the computer will iterate this until it's all the way down to 1 cluster of 600 people. So the computer gives you the printout, but it doesn't interpret it for you. So now you have to go in and try to offer some interpretation to, do I feel like I have 2 clusters in my class, 3 clusters, 6 clusters? What would be your basis for doing that? So there's all kinds of assumptions you can make, things you can toggle on and off if you're doing this in SPSS, so you really have to think about the choices you're making here. We used Ward's method, which tries to maximize similarity over differences. So you're trying to put people where they're closer to these people and maximize their difference from other people. We used a squared Euclidean distance so that negative distances have a positive magnitude, so we're only comparing that. Hierarchical, agglomerative means that once 2 individual people are put together in a cluster, you can't undo that. It's hierarchical, and it just keeps agglomerating until they're all in 1 cluster. There are other ways that you can do cluster analysis. This is the method we chose here. So now I took that data, this is the same data I showed you before, that was just all in blue, and now I've color-coded it by the 4 clusters that we saw in our data. Okay? And it may not, when we gave them horribly creative names of low, mid, high, and change. And it's not apparent why that is in the cognitive, but I'm going to show you the affective pre-post. Okay? So we have students in the blue who come in with low expectations, and those low expectations are met. We have students in the green who come in with high expectations, and those high expectations are met, and then there's a group in between. And then we have this purple group, which we call change, because when you look at them numerically, they don't have much difference in terms of expectations than the green group. Mathematically, their mean is about the same, but they have this precipitous drop. Their experiences are very different than their expectations. There's a change for them, right? They're off that y equals x line. And then here's the C/A, which is always this muddled mess in between. So that change group really got us thinking, like, what happens to those people? Where are those the people who drop and don't take OChem? Like, should we focus our intervention on those change people? Like if we can identify those people at the beginning of the semester by giving them the millie, what can we do pedagogically to support them in form of an intervention? So we started wondering about this, did we meet your expectation? And first we tried to do this 2x2 analysis, and then we realized, wait. Some of these expectations that get fulfilled are not good. Like if you expect to focus on procedures, not concepts, and you're telling us, yep, that's what happened, we would prefer that that not happen, right? So it was problematic to do this, and if you didn't expect it, and it didn't happen, is that good? Is that bad? Like if you didn't expect to think about the molecules and that didn't happen, do you even have the perception as a student that that would be problematic for your chemistry education? Right? It's hard to expect things to happen that you can't even conceive of as possible. So we created these graphs instead by cluster. So the x-axis down here at the bottom, it says 1, 2, 3, 4. That's low, mid, high change on every one of these. And we have expectations in the blue, the pre, and experiences post in the green. Wow, to my eyes, those greens look different. That's got to be your projector. Like, that's kind of, they're the same green in my PowerPoint. So we started looking at this by cluster. And so you can see for each cluster of students, they expected to feel unsure about the purpose of procedures, but their experiences exceeded those expectations. Even the students who said, no, I don't really agree with that, it happened at a higher frequency than they expected. I expected to develop confidence in the laboratory, and I did. Right, so if you look at the high and the change, they don't look very different. They have this expectation they're going to come out confident. Something's happening to that affect, particularly for this group of students. What is that? The feedback they're getting from their TA in class, the professors' questions on the exam, like why is that confidence being shattered for some of them, but not all of them? If we could figure that out, that'd be great. I expect to think about what the molecules were doing. Yeah, that didn't happen for the clusters as a whole. So that was Miami data. And I said, oh, we got to look at this at other places with different pedagogies, different curricula. So we undertook this massive study across the United States at a variety of institutions, Gen Chem 1 and Gen Chem 2, and we asked them for this. Will you have your students answer millie for us pre and post? Will you have your faculty fill out the survey that Marcy created about what their goals are? And will you send us a copy of your curriculum so we can use the rubric to characterize it? So we wanted to triangulate on this idea of goals, curriculum, students' expectations, and experiences. It seemed very clear to me, dear God, I didn't know what I was doing, in terms of how much data that was going to be. So I had to bring in like an army of undergrads to help me with this. This is what we got for the cluster analysis of the Gen Chem 1 across the country. So the top half is the graph, the bottom half is the numbers, whichever one appeals to you, it's the same data for 2,800 students. And what shocked us is that it looks exactly the same as what we got at our institution. Didn't matter what the pedagogy was. Didn't matter what the curriculum was. As a whole, in our country, we still had these same groups of students.
Does the distribution of schools cover schools perhaps less selective than what you've described?
There were 8 R1s, 5 comprehensive master's institutions, 1 liberal arts college, and 1 community college.
Were you able to do this interdisciplinary, or has it been done interdisciplinary?
It's not. We've only done it in chemistry. I think the millie is begging for other people to make a physics version of the millie or whatever it looks, the field version of the millie. So this is just chemistry data. Then we did OChem. So here's the Gen Chem. What happened in the OChem? What's different?
The change group is almost absent.
Change group's gone. Right, so the easy conclusion there is they did leave. We didn't actually know that was true, but it suggests that possibility, right? It also suggests that even students who've had a year of college laboratory in chemistry still have low expectations when they come in or still have high expectations, and we still have this distribution of meeting them or not meeting them. Okay, so we wanted to do a longitudinal study to see if we could track those people that we thought disappeared. So these are almost impossible to do, as I joked about earlier, but they're sort of the gold standard. It's hard to get funding from NSF to do longitudinal studies because if I want to track cohorts through a 4-year degree, a 3-year or a 5-year NSF grant is going to run out long before I can do that. So funding models would actually need to change to support this kind of research. We make that argument in the Deaver report. Okay, so yeah, we make that argument in the Deaver report. So we decided to do this at our own institution where we had the highest hope of actually finding these human beings and keeping track of them. So we collected data at 6 points in time. Before they started Gen Chem 1, at the end of Gen Chem 1, at the end of Gen Chem 2, before they started Organic 1, the end of Organic 1, and the end of Organic 2. And so you can see our numbers in each of those points range from a low of 238 respondents to a high of 654. But then we had to try to match the data, and we ended up with 268 people who had answered it at least once during Gen Chem and at least once during OChem, and 61 people who'd actually answered it all 6 times. So now the chemist in you takes over and you think, oh, 61, that's way too small, I can't do anything with 61 people, right? But you can actually do a power analysis to figure out how many comparisons you want to make, what level of confidence you want to do. And we actually only needed 20 people to do this at these 6 data points. So we had triple the size of the sample that we needed. And here is what they look like in terms of their cognitive and affect. Oh, I didn't mean to do that, okay? So this is what they look like at the start of Gen Chem. Well, this is the, I'm sorry, what do I want to say? This is what that cluster analysis looks like for them at the start of Gen Chem 1. Their cognitive and their affective, right? So we have all 4 clusters, we have what we need to follow them. And then we did a repeated measures ANOVA where our between group variable was which cluster they belong to, and our within group variable was over time. Okay? And so I'm just going to end here by showing you that what happens to them. This is their cognitive. You can see it decline. And then do you see that it resets for OChem? They have this experience where it gets worse, and then all of a sudden, new course, new year, it's going to go better. The affect does not make that recovery, and the C/A is in between. So this would suggest that there's some really complex things going on with students' affect, the change from Gen Chem to OChem, and we need to do more study there. So I can see that I'm out of time. Sorry, I've been babbling too much. I'm just gonna skip, if I can get, there we go. If I can get, we gave data to faculty about what they wanted to have happen, and I promised you the story about worry. Some faculty said, I want my students to worry about their data, the quality of their data, because they want students to learn how to decide, is my data good? Do I need to repeat my experiment? Other faculty said, no, I don't want them to worry about the data. I'm going to take all the worry out of them. The experiment's going to work perfectly if they just follow my directions and do exactly as I say. And so we learned that even some words like worry can have this double meaning where it can be both good and bad for faculty. So I'm not going to show you the faculty data because I went over time and I do want to be respectful of that. So I just want to say in conclusion that our data suggests that students come in with high cognitive expectations in chemistry laboratory, but they go largely unfulfilled. Students view that purpose of laboratory as that we're measuring how well they can follow somebody's instructions that were made decisions by somebody else. It's like a cookbook. And they're painfully aware that they can go through lab without thinking about what they're doing and still get a decent grade on their lab report. Expectations for learning tend to dictate their experiences, right? If you don't know something's going to happen, you can't recognize it when it does, and that we should be paying more attention to to affect. So with that, I want to thank all the faculty who gave us access to their students and the students for being brave enough to tell us what is and isn't happening in their lab. These are my students and colleagues here on the left-hand column, and Marcy and her team on the right, and the NSF for their very generous support of our research, and you for your time. Thank you.